Good morning, everyone. Um, yeah, am I
Morning.
audible? Okay. Just before we start off with the class, some announcements. So you must all have received your marks for the first assignment. So it's been graded, and the solutions have also been uploaded. Okay. Yeah, being like liberal to the extent possible. Okay, so if you have lost some marks, there would be a solid reason for it. So before you approach the TA, ensure that you've gone through the solutions, just to be sure where you've lost marks. I mean, it should be evident once you go through the solutions. Okay, and also use these solutions as a way to figure out where like if you've made mistakes, to understand the right solutions. That's the whole point of uploading these solutions. Okay, so hopefully that should help you for even in your preparations for the midterms. Okay, so the midterm exam, I hope you have all got the announcement now from the academic section. So it will be on next Saturday. So it's on March 20, right? So not the coming Saturday, but the following Saturday at 10 a.m. Okay, so it's a 2-hour exam, and it's going to be open book. Okay, so I will expect you all to turn on the videos at that time. You have to turn on your videos. Okay, so we want to ensure that we can see what you're doing. So I was initially thinking of keeping it as a theory and also with some programming exercises. But then I thought maybe it is like for a 2-hour exam, maybe it is too stressful to keep programming components. So we'll just have it as a theory exam this time. Okay. Yeah, and of course you would have got these announcements that copying is not acceptable. No form of plagiarism is acceptable. So that is equally valid for this course as well, and we take it very seriously. Okay. So now another announcement I wanted to make was about assignment 2. So there are some updates in the data set. So the earlier data set that I put up, for some reason it got corrupted. So I put up the newer ones. You must have seen a comment for that. So ensure that you have taken the latest data set. Okay, and for this, there are some programming parts even here for this assignment. So here you can't use solvers. Okay, so in the previous assignment, I asked you to use some solvers, but for this assignment, since you've already learned some of the techniques, you have to use the techniques that you learned in class, and you have to code the optimization methods yourself. Okay, so you can like some operations like matrix multiplication, inverse, norms, those things you can use the function supported by MATLAB or Python or whatever you're using. But by and large, the algorithm has to be coded from scratch, I mean, even including the gradient and Hessian computations. Okay, that's one thing. And there's also in question 6. So maybe I should just start presenting the screen now. Yeah, so I hope the screen is visible. So,
Yes, ma'am.
okay. So there's this question on logistic regression. So here, I've just given in the data set, if you've seen, it's a 2-dimensional data set. So the X's have 2 components. But if you're going through some of these logistic regression theory, like you will see that, the usual practice is to augment this X with one more value, a constant 1. So that, the linear term that you have here, you can have a W0 plus W1 X1 plus W2 X2. Okay, so that's the usual way to do it. So I've not explicitly mentioned it here. So for this question, it's okay. I mean, even if you don't augment that 1, it's fine. If you augment that 1 also, it's okay. So either way is fine. Okay. So yeah, I just wanted to mention that point. Okay. All right. So yeah, so I think now let me start off with the class. Okay. So in the last time we were looking at LPs. Okay, we started going through some examples of linear programs, and we saw a way to solve an LP geometrically. Okay, so it was sort of this way in which you write out the feasible region, like you characterize it. It's a polytope most often. And you also try to write the contours. Okay, so the example this was the example that we saw. You try to chart out the contours, and then you see how far, like what is the direction in which you need to go. Okay, and you try to keep going, like the contours. I mean, here the direction of the gradient was in this way, the c vector was in this way. So what you would do is, it's a minimization form, so you wanted to go in the other way, and you try to see how far you can go. And that's when you came across this point. This was the best you could go to, and that's how you report the optimum solution. Okay, so now in general, you can use this technique not only for linear programs, but even any constrained optimization problem. This is a method that you could use. Okay, so suppose you had something like minimize x1 square plus x2 square. So then you would have these circular contours, something like this. Okay, and of course the minimum would be at 0, 0. But I mean, the same technique you could use. Instead of these linear contours, you would have circular contours here. Okay, so this geometric method works for any kind of constrained optimization problem. Okay, but the thing is that it has to be like 2 dimensions. More than 2 dimensions, yeah, it's not very clear how you would visualize it. Okay, so so there was also this question about, if these inequalities were like they were strict. Okay, so if it's not less than or equal to, but if you had something like this, so of course most often you want to avoid these kind of things, because we'd seen earlier about these infimum not being achieved and so on. Okay, but one thing to note is, for example, in this particular problem, okay, so the optimum was at this point, this 1, 1. So suppose you had the constraints were basically these, right? So x1, these less than or equal to, and x1 greater than or equal to 0, x2 greater than or equal to 0. So of course, there's one thing that, if x1 is strictly greater than 0 and x2 is strictly greater than 0, what you would have is again the same region, but these boundary points of these axes, these won't be there. Okay, so in that case also, for this particular problem, since this is going to be the optimum, so it doesn't affect, okay, that if these inequalities became strict. But of course these have to be less than or equal to, otherwise you won't get the solution, the infimum won't be achieved. Okay, so there are some exceptions like this, but it's not always easy to figure out this. Okay, so that's why always you always write it in this way, like less than or equal to or greater than or equal to. Okay, so so with this, let me come to what is called the standard form of a linear programming problem. So we saw that, in LP you can have in the feasible region you can have inequalities as well as these equalities, and you can have things like x greater than or equal to 0, or even that can be relaxed. Okay, so now the particular form called standard form of a linear program expects the LP to be written this way. Okay, so the objective function is linear in the x's. Okay, and the constraints are of this form, ax equal to b. So not ax less than or equal to, not ax greater than or equal to, none of those forms. It has to be in this way, ax equal to b, and x's are greater than or equal to 0. So both these are essential to the standard form. Okay, and of course this minimization is also of something that we insist on in the standard form. Okay, so the reason is simple, that many approaches for solving linear programs make use of what you know about solving the system of equations ax equals b, and then you're trying to gradually build upon what you know of the system with additionally x greater than or equal to 0 and the optimization problem. Okay, and minimizing this. So that's why this is most often this is the most common way to write the LP. Okay, so it turns out that of course if you have it in different forms, so suppose your LP or whatever you formulated had this form like ax less than or equal to b, you can bring it back to this form ax equal to b. Okay, so how would you do that? You would just add some new variables okay, some y's, so as many as the number of equations, and you will just augment this ax plus y equals b. Instead of writing that is less than or equal to, you just add a positive quantity here. So these are the two things. This is how you would modify the system. Okay, so let's just take an example. So minimize something like x1 plus x2 such that x1 plus 3x2 less than or equal to 1, and 2x1 minus 5x2 less than or equal to 2. Okay, some random stuff. Okay, so and all the x's are greater than 0. Okay, so how would you change this to this form? Ax equal to b. Can someone tell me?
x1 plus 3x2 plus y1 equal to 1.
Equal to 1. So y1 equal to 1. Yes.
And similarly 2x1 minus 5x2 plus y2 equal to 2.
Okay, plus y2 equals to 2. And you have x1, x2 greater than 0.
And
And
y is also greater.
y's are also greater than 0. And the same thing, right? Minimize x1 plus x2.
This one.
Okay, so yeah, so these variables are called slack variables. Okay, so because they are introducing they're capturing the slack in this in these inequalities. Okay, now similarly, if you have something like ax greater than or equal to b, you could do the same thing. You could do a similar trick that you just add these y's. I mean, you just remove the y's now. Ax minus y is equal to b, and all the y's are greater than or equal to 0. Okay, so that's it's just a symmetric trick. So these variables are called surplus variables. Okay.
And
Now,
then just to confirm, we can have slack variables and surplus variables in the same program, in the same
yes,
question as well.
yes, you can have a combination of these coming in. So you can do this trick for each of those inequalities. So that's fine. Okay. Yeah. So now,
Do,
yes.
do we need these plus variables, or we can only work out with these slack variables? Suppose I do it minus ax less than equal to minus b, then it would be fine with only slack variables. I
Yeah,
don't need to define these new
yeah,
variables.
yeah. That's also fine. You can also change it, modify it in that way. Right. That's also acceptable. That's okay. Okay. So, yeah. So now, yeah. Another thing is, I mean, the other point which comes in is this x greater than or equal to 0. So many times you may not have that in your formulation. Okay, so to take care of that, if you don't have this x's as non-negative in your original formulation, what you could do is you can add these additional new variables x plus and x minus, so these are greater than or equal to 0, and then you write x as x plus minus x minus. Okay, so a positive component as well as a negative component. Okay, and these two are greater than or equal to 0. Okay, and so wherever x comes, you just replace it with x plus minus x minus. So ax equals b is just going to become ax plus minus ax minus equal to b. Okay, so you have completely eliminated this x, and it's a new system with just these new variables. Okay, and even the objective you have to modify it so that you only have x plus and x minus. Okay, so yeah, these are some ways in which you deal with it. Okay, deal with these various aspects to convert it to a standard form. Okay, yeah. So one thing about Rajnish's question with respect to, I mean, the reason why you add these as surplus variables, it's just like traditionally, they used to insist that B has all entries as non-negative as well. Okay, so now when you change the sign, if you change the sign of these inequalities, it becomes like a negative quantity, right? So that's the reason it was, the surplus variables were, separately introduced. But yeah, in principle, you could do the same trick for both. Okay. Right. So, okay. So now, so from here on, like we will try to, we will stick to the standard form, and we will do the analysis with the standard form LPs. Okay. Now, in general, you remember, like when we talked of unconstrained optimization problems, we looked at different scenarios, right? Like about the problem being feasible, the problem being unbounded, bounded, and so on. So LPs are also no different. You're going to have the similar kind of situations here as well. So a first example is when the LP, you say it is feasible and bounded. Okay, so what that means is, the constraint set given here, there's at least one feasible point, and it's bounded in the sense that you will hit a minimum point. Okay, so that's what it means when you say the LP is feasible and bounded. Okay, so an example is this one. Okay, so minimize x1 minus x2 with the x's non-negative, and you have x1 plus x2 less than or equal to 3. Okay, so I've just drawn this figure to illustrate the region, the feasible region. So this is actually, yeah, it is a region. I mean, of course, you have at least one feasible point here, and for this LP, the minimum is achieved. It's a bounded and feasible region, and the LP itself is bounded in the sense that the objective function will not become minus infinity, right? There'll be some point at which you will have to stop. Okay, so that's a feasible and bounded LPs. So this is like the best case, right? Like you always like to have this kind of things where you can get an optimum solution. Okay, now another thing is feasible and unbounded LPs. So something of this form. Okay, so minimize x1 plus x2 such that x1s are all greater than 0, but x1 plus x2 is less than or equal to 3. So now x2, there is no constraint. There's no non-negativity constraint. So the feasible region is something like this. So this is the line x1 plus x2 equal to 3. Okay, so you have this side of the LP, this side of this line, which is a feasible region, and you have x1 greater than 0. So basically this side of the y-axis, and of course the whole part of x2 is allowed. So x2 can go as small as possible. Okay, so it's basically this huge unbounded region here. Okay, so here if you see, I mean, even when you try to minimize this x1 plus x2, you're going to, whatever value you say as, if you say that some value z is the minimum, you can find something even lesser, which is the minimum, and which is also feasible. Okay, so yeah, so here one thing to note is that this is a function of two things. One is the feasible region itself, and the feasible region has to be unbounded first, and also something about the objective function will make the LP itself unbounded. So for example, you can try to see what happens if you, instead of this, suppose you had x1 minus x2. Okay, so just think about what happens in that case. I will leave it as an exercise for you. So in that case, you will not have, you will have it will come to the case where the optimum exists. And the optimum is not infinity. Okay, so it's not negative infinity. So so what I want to just highlight here is that it depends on two things: the feasible region itself, as well as also the objective function. Okay. Now, another case is when the case of infeasible linear programs. So something like this: you have x1 plus x2, which is less than or equal to 3. So that is basically, this is the line x1 plus x2 equal to 3. Okay, and you have basically this side of the line, and the other constraint is x1 plus x2 greater than or equal to 4. So basically you have this part, right? And you have x1 greater than or equal to 0, x2 greater than 0. So now basically everything in the first quadrant. Okay, so basically all these part, that is the so it should satisfy both these simultaneously. Okay, so that's not possible, right? So that's why this is an infeasible LP. So there's nothing, you cannot find any point here which satisfies these constraints. Okay, so these are the possibilities that you can have for a linear program. Okay, so now when you try to devise any algorithms, you should also take care of identifying when of course this first case is what you would like to achieve. You would ideally want this, but you should also have a way to figure out when these other cases occur as well. Okay. So any questions still here?
No, ma'am.
Okay. So I hope it's clear to the rest of you as well. Okay. Okay. So now let's try to think of, let's try to build a way in which you can get some solutions. I mean, not geometrically, but if you have higher dimensions, a more general way to solve LPs. So for that, we will look at what is called a basic solution. Okay. So the method that we will adopt is, you slowly try to build the feasible region and then try to see what happens with the objective. Okay. So now let's just look at the system of equations Ax equals b. Okay. And here we'll assume that A is of size m cross n with the value of n much larger than m. So basically something like this. This side is it's a wide matrix. Okay, so you have few equations. Okay, so you have about m equations, but the number of variables is much more. Okay, so we will focus on this system, and the rank of A, we'll assume it's m. So in the sense that all the equations are giving you something useful. Okay, so there's no redundancy in terms of the equations. Okay, so now like what do we know? Suppose we had like this is a huge system, so there are so this much is m, and here you have some more columns here, n minus m. So suppose you had an alternate system where you only had some m, a matrix of size m. Okay, so what I mean is, suppose you had a case where there's an A tilde which is of size r m cross m. Okay, and suppose this was of rank m. Okay, so that means all the equations, all the m equations are meaningful, and the number of columns is also exact. So you have as many equations as the number of variables, and all these equations are adding value. So in that case, if you had a system like say a tilde x equals b tilde, so then what can you say about the solution x?
Unique single solution.
Unique single solution, right? So you can just compute this as, so A tilde is going to be invertible, okay? And you're just going to have something like this, right? A tilde inverse B, okay? So for this case, you know a way to solve it very clearly, okay? So of course, Ax equals B, we have already seen other ways like Gauss elimination and all that. So yeah, so much of this thing is going to be built on what you know for this case, for this case where you have like m equations and m unknowns. Okay, so now if you use that same idea here for the case where A is a bigger system with more equations, more variables than equations, then what you can do is you can split this into two groups of columns. Right. So suppose there are these columns of A. So divide this into two groups B and N. Okay. So B is a system of size m cross n. Okay. So you're taking some m columns and calling them B, and the remaining ones you're calling them as n. Okay. Now suppose additionally that B is of rank m. So all the columns of B are linearly independent. Okay. So then if you write it this way, similarly, you can also group these x variables into two. Okay, so xb's which correspond to these columns and xn's which correspond to these other columns. Okay, and yeah, so you can just rewrite this as bn times xb xn is equal to this b. Okay, so all I'm doing is I'm just arranging them such that some of these linearly independent columns come together, and there are m of them. Okay, because this is of rank m. Okay, so now if you can do this, one way to just read off the solutions is by putting xn equals 0. So you can just say these variables, you make them 0, so that this doesn't come into the picture, this matrix n, okay, which consists of linearly dependent columns possibly, that doesn't come into picture. And then you have bxb equals b. Okay, so remember this B is a full rank matrix, and there are exactly m such columns, and xb also contains m variables. Okay, and so now this exactly is like this system, right? You can immediately, it's a unique solution here. So you can say xb is b inverse b. Okay, so this is one way to construct a solution. Okay, and so this kind of a solution is called a basic solution. Okay, so in particular, you have this division of these columns of A into two parts. Okay, and the variables corresponding to these second part, these are all zero, and the only non-zero variables correspond to these columns. Okay, so this kind of a solution is called a basic solution. Okay, so is this clear what we are doing here?
Yes, ma'am.
Okay, so what about Rohit is clear. So what about the others? Just type in the chat box, or if you have any questions, please do ask. It's clear, Bhavna, it's clear. Okay.
Ma'am,
So,
sometimes will we be able to separate it into two such matrices? It might be the case that these columns are interspersed, like not really onto right and left or something.
yeah, so that can happen, but of course you can, it is just like bringing these together, right? Like it's just like changing the order in which the variables are written, right? So
I
right,
think
so
the question was that if there are lots of columns, finding which of
mhm.
those m columns are linearly independent, that would require some trial and error or some. It would take
Yeah, of
time.
course, at this point we are not telling you how to compute these kind of solutions, but what I'm saying is that you can have, I mean, there are solutions of this form, right?
Yes, ma'am.
Right. Siddharth, was your question answered?
Yes, ma'am. I think you answered it. Like my question was that only, that if bringing right and left. So I think okay.
Yeah.
Broad.
Yeah. So at first you may have, like, things are spread out. You might not have all the linearly, like you can have things like the first two columns were linearly dependent, and maybe some other independent columns come later on. So that is fine. You can still rearrange the matrix. Okay, so that would just mean the x's just get swapped across. Okay, so yeah, so in general you can bring it in this form finally. Okay, so the focus here is not specifically on the ordering, but in the sense that you can find this kind of a grouping. I mean, maybe it could be like you have this matrix readily available to you as a contiguous form, or you can pick some of the linearly independent columns, in which case they're spread out, but there is a representation of this form. Okay. Yeah. So any other questions on this? I hope it's clear to all of you. Okay. Okay. Okay, so now, so this was one way. I mean, so the whole thing is we are trying to connect it to what we know about AX equals B. Okay, and when we have unique solutions, so that's why we're trying to extend that idea to the feasible region of linear programs. Okay, so these are basic solutions. Now, in the process, it could also be that some of these XB variables, right, even those can end up becoming zero. So xn, these you fix them as zero, but in the process of solving this, it could be that some of these xb's are also zero. Okay, so then so it depends particularly on the small b and also this basis itself. Okay, so then in that case, what you have is a degenerate basic solution. Okay, so sorry, this is a degenerate basic solution. Okay, if some of the xb's also become zero. Okay. Now, so when we wrote this basic solutions, we only looked at Ax equals B. Now, in the standard form LP, you are also going to have x greater than or equal to 0. So So now when you solve this when you get a basic solution, if in addition it also has these x's are greater than or equal to 0 for all i's, then what this is called is a basic feasible solution. Okay, so you have basic solutions where the x's can take any values. Only restriction is that you can divide it into two groups of variables, and with one set of them will take a value exactly 0, but xb's can take any value. It could be positive, it could be negative, and so on. Okay, now if in addition these xb's are also greater than or equal to 0, then what you have is a basic feasible solution. Okay, so this this is coming from the notion of basis, right? So this B is actually, it is a basis, right, for Rm, because there are m linearly independent columns. Okay, and they form a span for the space Rm, so it's a basis, and so the solution is written with respect to some basis. Okay, so that's why it's called a basic solution and a basic feasible solution. Okay, so let's just see some example of this. So I have these set of equations here. Okay, so suppose this is the feasible region, and I also have x1 greater than 0, x2 greater than 0. Okay, so now I would convert this to standard form first. So that would be by using something like this, right? x1 minus 3x2 plus y1 is 23, right? And what's the other one?
x2 plus y2 is 4.
Y2 equals 4. Okay, and
y1, y2 greater than 0.
yes, x1, x2, y1, y2 all are greater than 0. Okay, so now, so if I write this matrix out, so the matrix A is got from here. So this is just 1 minus 3, 1, 0. Okay, that's the first equation. And the second one is 0, 1, 0, 1. Okay, so you have, this is the matrix A. Okay, and to write it compactly, I'll have something like this, y1, y2. So this is the system, and here you have 23 and 4. Okay, so now if you look at this, so immediately you can tell a basis, right? So this part, so these give you two linearly independent columns. Okay, so this can be the basis B, and this can be the remaining part N. Okay, so two equations, so you need a 2 cross 2 system for B. So that's what this is. Okay, so then this will correspond to what? So for these two columns, so x1 corresponds to the first column and x2 corresponds to this column. Now y1 corresponds to this and y2 corresponds to this. Okay, so if you want to write the basic variables, that would be these two. Okay, so the basic variables here are y1 and y2. Okay, and the non-basic variables are x1, x2. Okay, so this is something that I will choose. Okay, so this is x1, x2. Okay, and so immediately the solution, one basic solution here is x1 equals 0, x2 is 0. So these non-basic variables can be set to 0, and y1 equals 23, right? So this corresponding to, you only use this reduced system here. So y1 is 23 and y2 is 4. So it's as if you're solving this system 0, 1, 0, 1, 0 times 1, 0, 0, 1 times y1, y2 is equal to 23, 4. Okay, so one immediate solution is this. Okay, and in addition, you have that all these variables are greater than or equal to 0. So this is also a basic feasible solution. Okay, it's a basic solution and also a basic feasible solution. Okay, now you can find different ways. So this B, this is not unique, right? So one other option is maybe you could fix these two. Okay, so that will give you x2 and y1 as the basic variables, and x1, y2 are non-basic. Now, even the first two rows, this itself, you can fix it as a basis, right? Because these two are linearly independent also. But the thing is, you yeah, that you will have to solve this systems separately. 1 minus 301, 23, 4. So that you have to solve it separately. The advantage of choosing this as a basis is it's readily available, because the basis here is just the identity. Okay, but of course, even there are so many basic solutions you can come up with. Okay, so I hope this example is clear. Any questions on the example?
As you said, there are multiple solutions possible, but only one of them will minimize the objective function. So, I mean, how do we pick that basis which results in minimum solution?
Yeah. So of course, only not everything will minimize the objective. So that will require some more steps. Okay. So at this point, we are only looking at the feasible region. Like, forget about the objective for the time being. Okay. So
Yes.
okay. So yeah. So we will come to that part. How you pick the optimal one. Okay. But is this notion of basic solutions and basic feasible solutions, is that clear to everyone?
Yes, ma'am.
So what about everybody else? Simran?
Yes,
It's
ma'am, it's
clear?
clear.
It's clear. Okay. Okay. Fine. Good. So this is one example. Now another example that I have here, I've just put one more thing. So x1 plus x2 is greater than or equal to 5, and x1 minus 2x2 is greater than or equal to 1. So here I'm going to include these surplus variables. Okay, so I've written this in the standard form in this way. Okay, so I just added two more variables, x3 and x4. Okay, so here also I have these constraints. Okay, x1, x2 greater than or equal to 0. Okay, so now the feasible region is something I've just drawn here. Okay, so there's one equation that x1 plus x2 is greater than or equal to 5. So that is this line, and you have everything basically on this side. Okay, and x1 minus 2x2 greater than or equal to 1, so something of this, and you can try to sketch it yourself, but let's try to look at this matrix corresponding to these equations. So you have this, right? So I'm just bringing it together: 1 1 minus 1 0, and 1 minus 2 0 minus 1. Okay, so here I'm going to again use this as my basis. So then what I'm going to get is, so x3 and x4. So this corresponds to x1, x2, x3, x4. So x3, x4 correspond to this basis. And here what I'm going to get is x3 is minus 5 and x4 is minus 1. And x1, x2 are 0. Okay, so this is a basic solution, but it's not basic feasible. Okay, because these values are less than 0. Okay, so that's the distinction between these two, basic and basic feasible. So we want always a basic feasible solution when we try to solve LPs. Okay, so the reason why we are doing all this is, it's just that if you look at the feasible region to linear programs, it's a huge set, right? It's there are infinitely many solutions, and it's not even countable. Okay, so you want to have some way to analyze it systematically. So that's why we are trying to go into these basic solutions and basic feasible solutions. Okay, so now we come to the main theorem of linear programming. So the fundamental theorem of linear programming, which says that if a linear programming problem has a feasible solution, there is also going to be a basic feasible solution. Okay, so basic feasible solutions is very unique way in which we constructed these solutions. So an existence of a feasible solution implies that, yes.
In the previous example,
Yes.
Why don't we do one such thing that we just make these four equations like x1 plus x2 plus x3 equal minus x3 equal to 5, and these two. With these two, we should have two more equations like x1 minus some z equal to 0 and x2 minus some p equal to 0. So we just have to solve these four equations. Now we don't have these constraints.
So you mean to say for these also you can put these slack variables, right?
Yeah.
I mean slack or surplus variables.
Yes, ma'am.
Yeah. So yeah, that you could do that. I mean, then it would go into a different way of analysis. It wouldn't come into these kind of basic feasible solutions. So now you will have to separately keep tab of the basic solutions. I mean, these notions, right? These basic and basic feasible that are particular to this form, where you include these only for these inequalities. I mean, you don't include these for these x1, x2 greater than or equal to 0 constraints. Okay, so the reason is just that, I mean, whoever tried to build these solutions, you try to analyze what you know about this system and try to address this issue separately. So okay, so that's why these basic and basic feasible solutions, they are defined in this manner. Okay, but if you're going to do that, then you will get a different notion of solutions. Okay, right? Is this okay, Rajneesh? Rajneesh is asked.
Yes,
Right?
ma'am. Okay.
Yeah, so of course there are different ways you can approach these linear programs. I mean, there are different ways to approach it, and so this is just one way. I mean, this is one of the common ways in which this is addressed. Okay, so of course it's not the only way. Okay, so right. Okay, so any other questions on this? Okay, you're
No,
quiet.
ma'am.
Okay. Okay. Yeah. So the reason why we looked at this is because precisely about this fundamental theorem of linear programming, which says that if a linear program has a feasible solution, there is a feasible solution. Okay, and if it has an optimal feasible solution, there is also an optimal basic feasible solution. Okay, so the effect of this is that as a consequence, you can only focus your attention on these basic feasible solutions. Okay, in order to do the analysis. So in order to try to find the optimal solution for the linear program, what you could do is you just focus on the basic feasible solutions and then try to find an optimal from them. Okay, so is the statement of this fundamental theorem, is it clear? Right,
Yes,
I
ma'am.
hope the statement is clear. Okay, so let's just see a small proof of this. So it will look quite similar to the Carab-Theodorese theorem that you saw earlier. Okay, so let's just start with if the linear program has a feasible solution. Okay, suppose it has a feasible solution, and let's call that feasible solution X. Okay, so A1, A2, AN, these are the columns of A. Okay, and so when X is a feasible solution, it just means that A1 X1 plus A2 X2 so on up to AN Xn is equal to B. Okay, and of course X's are greater than 0. That's also there. Okay, and yeah, so it's basically this column representation of the system of equations. Okay, so now this is a feasible solution, and what you're trying to say is there is a basic feasible solution as well. Okay, so what we'll do is we'll try to construct a basic feasible solution using this X. Okay, so now in this X, let's try to analyze this X. First thing is to see, this is a feasible solution. Is it already a basic feasible solution as well? Okay, so to do that, so you see that suppose P of them, exactly P of them take a value greater than 0. Okay, so there are n variables, so n minus P of them are equal to 0 and P of them take a value greater than 0. So let's call it x1 to xp. Okay, without loss of generality, you can think of them as the first P variables. Okay, so the rest of them are 0. Okay, so now what it means is you can restrict your attention only to these columns A1 to AP. Okay, because the rest of the columns don't play a role. So A1 x1 plus A2 x2 plus so on up to AP xp, this is going to give you B. Okay, so now if these columns are linearly independent already, so this A1 to AP, if they are linearly independent already, so then that gives you, so then X itself is a basic feasible solution. Okay, because if they're linearly independent, then by definition you cannot have that this P is greater than n, right? Because these are all vectors a1 to an, they're all vectors in Rn. Okay, and so if a collection of linearly independent vectors, you cannot exceed n. Okay, so they have to be less than or equal to m, the number of such vectors. And if they are less than, so if they are linearly independent, then that's it. This is the basis. So the columns corresponding to a1 to ap, that is the basis. And x1 to xp become the basic variables, and the remaining are the non-basic variables. Okay, so that is done. That is the case where x itself is a basic feasible solution. Okay, so now suppose not. So if they are not linearly independent, so what we have till now is exactly p of them take a value greater than 0. So this is true, but these p are linearly dependent. Okay, so then the idea is that you can, not all of them are important to construct B. Okay, so you can eliminate at least one of them. Okay, and you can keep doing this till you reach, m, till you set P equals m. So this flavor is kind of like the Carat-Theodorese theorem. Okay, so a formal proof is like this. So if they are not linearly independent, so that means you can find some other numbers, y1 to yp, not all of them are 0, such that this linear combination gives you a value of 0. Okay, so so then the idea is to use these this equation, these y's along with this system to eliminate one of these columns. Okay, so one thing to note here is that at least one of these values, y1 to yp, will be strictly greater than 0. Okay, a linear combination of them is giving you 0, and not all of them are 0. So you will have some things which are positive. You'll also have some things which are negative. Okay, so at the point is at least one of them will be greater than 0. Okay, and so you make use of these two equations, 1 and 2, to together eliminate one of them. Okay, so how would you do that? It's just an algebraic manipulation. So you just subtract some multiple of the second equation from the first. Okay, so if you multiply this with some epsilon, okay, we'll come to what that epsilon is. So if you multiply this with epsilon, and so you'll get epsilon times a1 y1 plus epsilon times a2 y2 plus so on is 0. Okay, and now you can subtract it from the first equation, and that's going to give you this. Okay, so now the way is to intelligently choose epsilon so that at least one of these variables disappear. Okay, so is it clear up to this point?
Yes, ma'am.
Okay, fine. So please stop me if something is unclear or it's too fast.
How did we say that we are using the same A's for getting 0 and getting B?
Oh, this one. So yeah, so okay, so A's are all what are those? Those are some columns of the matrix, right? So these are a set of P columns. Okay, and this is given to you from the feasible solution. Okay, so this part is clear, right? How we can use this feasible solution to write B. Okay, now of course, like since they are not linearly independent, so if you take any set of columns, you can construct 0 trivially, right? You can write you can just put all these as 0, y1 y2. So these are different from x. Okay, so these are some different combinations, and if you put all of them as 0, that will give you 0 for sure, right? But the point is there is something other than the zeros here. Okay, so there is something other than setting all these y1 to y and yp's to 0, because these are all linearly independent. So now we are going into this track where a1 to ap's are there is some dependence among them. Okay, so because of that, you can write this representation, okay, where all the y's are not 0. Right? Siddharth, Is it clear?
Yes, ma'am.
Okay.
Ma'am, what we
Yes.
exactly want to achieve here
In this part, so
by
the
this proof, by this whole thing, by all this whole thing, what we exactly want to achieve?
So what we're trying to say is, if you, so we saw about these basic feasible solutions, right? So is it always that you will have a basic feasible solution? Okay, so or rather, when will you be able to construct a basic feasible solution? Why are we looking into that? Okay, so that's why we are looking at this kind of a proof, which says that if you have a feasible solution, you have a basic feasible solution. Okay, so if there's a feasible solution, there's a basic feasible solution. So what we are trying to say
In terms of matrix, yes, ma'am. This x1 to xn. In terms of this x1 to xn, what we are trying to do here?
in this part, in this this whole all
Ma'am, we
these
are trying to
steps.
achieve a basic feasible solution for a feasible solution.
Yes,
So what
yes.
does this statement mean in terms of x1 to xn? You're
So
trying to
this
find some
one,
more xi's as to be zero or what?
yeah. So one thing we have is this one. Okay, this one is given to us. Now, using this, so here there's no connection with the x's. Okay, so this is just a combination of them, which is going to give you 0. So now what we are going to do is we are going to construct another basic feasible solution. We are going to construct a basic feasible solution using these x's and these y's. Okay, so yeah, so maybe let me maybe I should just complete it, so then maybe things will get clearer to you. So okay, so this comes from the feasibility, and this comes from the linear dependence, okay, between these. So the point is, you can make use of both these x's and y's to construct another basic feasible solution. Okay, so the way you do that is by this is another solution, right? If you multiply this with epsilon and remove that from x, so these x minus epsilon y's, this is another solution to ax equals b. Okay, so x minus epsilon y, so you will have this is true, ax minus epsilon y is going to give you b. Okay, so now the thing is, you cannot choose any epsilon here because you additionally want that x this thing that's constructed here, this new point constructed, should have all the entries as non-negative. Okay, so that's why the epsilon has to be chosen wisely, so that all these numbers are greater than 0. Okay, greater than or equal to 0. Okay, and so for that, what you will do, so now if you can achieve that, what you will have is that this is another solution, but hopefully one of these will become 0. So suppose this one becomes 0, you will have another solution where there are p minus 1 of these columns which are which are being used, and everything else is 0. Okay, so that's the idea. Okay, and so the thing is to see how you can make one of these entries, xi minus epsilon ys, how can you make one of them 0? Okay, so for doing that, and I mean, you want to make one of them 0, and also you want to have that all these entries are greater than or equal to 0. Okay, so for that, what you do is, it's a particular way of choosing these epsilons. Okay, you just take the minimum value of xi minus yi, xi by yi. So then when you you look at all the y's for which these yi's are greater than 0, okay, and then you take this minimum value here. Remember, x's are all greater than 0, greater than or equal to 0. Okay, so in particular, they are greater than 0 here. Okay, so that's what we assume. Okay, so now when you take xk, so let this happen for some I equals k. So this particular I for which epsilon is equal to xi by yi, so that is equal to k. So let me just write it here. So epsilon is actually equal to some xk by yk for some k. So that's what this means. So then if you take xk minus epsilon yk, you're going to get 0 here. Okay, so then what you have is, in this expression, if you plug in this value of epsilon, at least one of them has disappeared. So what you will get is a reduced system, like a1, so some x1 tilde. So let me call this, let x tilde be x minus epsilon y. Okay, so a1 x1 tilde plus so on plus a k minus 1 x k minus 1 tilde. Now xk, this is gone, this is not there, so you'll get ak xk tilde plus so on plus ap xp tilde, this is equal to b. Okay, so you have eliminated one of them in the process, and you also should check that all other uh, quantities are going to be greater than or equal to 0. Okay, so that's going to happen because this epsilon was chosen as the minimum for which this is the minimum value of xi by yi. Okay, so that is going to give you a system where you have a dependence on p minus 1 linearly independent columns, and you can keep doing this till you reach n. Okay, at each step you can keep removing it till you get n linearly independent columns. Okay, so I don't know if this was clear. Are there any questions on this?
Ma'am,
Rajneesh? Yeah, Rohit, yes.
ma'am, just to confirm, the first scenario was where we had say the rank is R, so we had exactly R variables that are linearly independent.
Mm-hmm.
The second scenario was that we had more than R variables. Sorry, we had first scenario was R variables are non-zero, and that is fine because there are exactly R columns that are linearly independent.
Mm-hmm.
The second scenario was that we are getting more than R variables to be non-zero, so we are trying to
Yes.
cut down some of those variables to get exactly R
Yes.
values.
Yes. So one thing I want to mention is the rank of this system is still exactly m. Okay, so this
Okay.
matrix A, the rank is exactly m itself. Okay, so
Okay.
what we are just trying to see is in terms of the number of solutions which are number of values of x which are greater than 0. Okay,
Okay.
so this can be either, it can be greater than m or it can be less than m. Greater than or equal to m or less than or equal to n, right? So the first scenario is where you have like at most m of them take a non-zero value. So the number of these non-zero things, this is less than or equal to n. Okay,
Yes,
so
ma'am.
that means you constructed B with less than or equal to m columns, and that is immediately giving you a basic feasible solution. Okay,
And the
now
second
that
scenario was more than M.
more than m, right?
And ma'am, what is then there'll be another scenario where the some of the x's that we are getting those are negative, right?
No. So we started off with a feasible solution. So that means this is true, and also all the x's are also greater than or equal to 0. That is true.
Okay.
Okay. So that, for the x's that won't happen, but you have to be careful when you construct this new solution. In the second part, where some of them are not linearly independent, now the new solution we are going to construct something as x minus epsilon y because we want to remove one of the components, right? We want to make one of these x's 0,
Yes, ma'am.
right? So by doing that, you should ensure that all these are also greater than or equal to 0, right?
Yes, ma'am.
Okay. So I think we are running out of time. So yeah, I will hang around here for any questions. But if you have some other class or something later, you may go now. Okay, because the recordings will be up anyway. But I'll be here for some time. Okay. Yeah. So thanks being here. Okay.
Thank you, ma'am.
Yeah.
Ma'am, could you explain how the notion of basic came? So I understood we started out with the feasible solution, but I didn't understand how we're showing that a basic feasible solution exists.
So in this proof, right?
Yes, yes, ma'am.
Yeah. So here, so you understand this part, like how we removed one variable, one x at a time, right?
Yeah, yeah.
You understood till this point.
Yeah, I understood all the algebra. I just like I didn't understand how like we started out with a feasible solution. So the idea of a basic feasible solution existing and that being different from the feasible solution.
Yeah. So we started off with a feasible solution, and now what we did till here is we eliminated one of the variables. So we made one more variable as 0, right? So here, if you take the other variables, right? So let me just write it. Okay, I'll just write it in a new page. Okay. So here, so we had this expression, and now x tilde is the new point that we got. Okay, so we started off with x. So in x, there were p variables for which xi was greater than 0. Okay, and for n minus p variables, you had xi is equal to 0. Right. Now, when you come to x tilde, this is a new point that we constructed. So here what is going to happen is p minus 1 of these variables are going to take a value greater than 0. Okay, so this is an x tilde, and you have an additional one here. So n minus p plus 1 variables take a value equal to 0. Okay, so that you have to check this. So now the point in particular constructed was x tilde is x minus epsilon y, where the y's satisfied this relation, right? So y's have exactly p components, and all the others, so yp plus 1 up to yn is equal to 0. Okay, so now similarly for x also, you have xp plus 1 to xn. So these are all 0, right? So now even in this solution for x tilde p plus 1, and so on up to x tilde n. So this is going to be 0. Okay, so like what we had for x. Now in addition, we have shown that in this case, there's one more variable which becomes 0. So for particularly the kth x, so x tilde k, this is also going to be 0. Is this clear? Devyani?
Yes,
This
ma'am.
is clear, right? Okay, so now, so this part is clear, I hope.
Yes,
Right?
ma'am. So the idea that we're reducing to the rank would be ideally what would indicate that the solution is basic. And
yeah,
because we're maintaining that each variable is like x tilde is always such that it's greater than equal to 0,
yes,
is what is
exactly.
making it feasible.
Yeah, so you have to keep doing this multiple times. So till you, so this is now you have p minus 1 of the linearly independent columns. So now till you reach m, you keep doing this. At each step, remove one point.
Okay, ma'am. And also, it wouldn't matter if we went to a degenerate case. So, like, we sort of reduced more than m, it wouldn't matter.
Yeah, that is okay. So that will happen in this case, right? If there are multiple case for which epsilon, so you have xk minus epsilon yk 0, and also some other k, xk2 minus epsilon yk2 is also 0. So then two things will disappear, right?
Yes,
So,
ma'am.
so that's okay. You can have a degenerate basic feasible solution. That's okay. All we're saying is you will ultimately reach a basic feasible solution.
Yes, ma'am. It's clear. Thank you.
Ma'am, does this basic solution help us somewhere? Why do we want means we just got feasible solution, so we should be happy after that.